Okay, so hello everybody. I'm very happy to be able to present to you today our paper on some approximate lookup tables and arbitrary function rotations for facilitating NISQ implementations of HHL and maybe other algorithms. This is work done by a student of mine called Petros Draganidis, who unfortunately couldn't make it to the conference, so I'll present his work. All right, so for a motivation, um, we basically often have the problem in quantum computing that somehow we need to encode our data. It might be classical data, it might be quantum data that is like in another form that should be encoded differently, and that's a substantial problem. And yeah, one small portion of that will be discussed in our paper here, how there might be improvements there. And for that, I'll revise a little bit something about the HHL algorithm that probably most of you know. Nevertheless, here's some details and mainly the core idea here. So the HHL algorithm basically solves the problem of linear system of equations. So AX equals B, where X is a thing that we want to find out, and A and B are given. And the core idea basically is that we can do eigenvalue decomposition efficiently on quantum computers using a quantum phase estimation. So this means that we can basically look into how this matrix A looks like and decompose it into its eigenvectors and corresponding eigenvalues. And now the cool observation that we can make is if we have A, it's not that hard to construct A inverse, because mathematically that's nothing but the same thing, but with the reciprocals of the eigenvalues. And now if we want to actually compute X in this case, then what we have to do instead of multiplying A with B, just like it is and how we could do it very natively, is that we have to invert basically those eigenvalues. And the core idea here is that we can write B in the eigenbasis of A. So this is beta. I is just a coefficient for the corresponding eigenvalue where this eigenvector which lives in the eigenspace of A, basically. So yeah, if we can just multiply the corresponding eigenvalue onto B, then we get A times B, and if we can do it with the reciprocal of that one, of the eigenvalue, basically, then we get the inverse, and that's the core idea, basically. In a circuit, we can do that in the following way. As I already discussed, we will write out B in the eigenbasis of A, and then we'll do quantum phase estimation, because we want to get the corresponding eigen values, which unfortunately in this case we get just as a in a basis state. Basically, it's a superposition of basis states. And then the next part here is basically just getting this eigenvalue out of the cat state, basically here, into the amplitude, which is done by firstly doing some arithmetic, basically. I have to invert that, then I have to do one more thing which we'll talk about later, and then after having it inverted, I have to get from this basis encoding basically into get the information from this basis here into the amplitude, which is usually done with the ancilla quantum encoding. And then in the end, we have our beta I divided by lambda I, and therefore roughly X. In the end, we have to do some uncomputation to make everything work. But yeah, that's the principal structure that this algorithm follows. If we take a closer look into this ancilla quantum encoding, we can see it's really nothing but fairly easy mathematical idea. So let's take some number that is written in terms of phi1 to phi n in like binary, basically. And this is assuming that this number is like 0 point, phi1, phi2, phi3, and so on. So we have a number between 0 and 1 written in binary with a floating point, basically. And then we take an ancilla qubit and we apply these controlled Y rotations, depending with the parameters here on, basically the position of the number that we are looking at. So this is the 1/2 position, this is the 1/4 position, and so on. And in the end, if we do the circuit, we can see that starting with this state phi and just an ancilla, we moved over to a superposition of being in 0 and 1 state of this ancilla. And for the 1 state, we can see we are in sine of phi over half, if we are very precise here. And actually, if we prepare that phi then in the right kind of way, which in the HHL means 2 times arcsine 1 over lambda I, we'll get out exactly what we want. We get out state 0, that is not interesting to us, but in the state 1, we get out 1 over lambda I, which basically, is exactly what we need for the HHL. So this is the core idea, basically, or the main functionality of ancilla quantum encoding. The thing now is, as you can see, we have to prepare our state in a weird way here, because we need this arcsine in there, basically. And even we need this 1 over x to be calculated, like, really arithmetically. And this here is a circuit which can do that, basically. It's taken from Tablier et al. And you can see this is already very, very complicated. We see adders and subtractors here, which itself need a lot of qubits and so on. And this is just the integer division. If we have to do the arcsine on top of that, the circuit is going to get huge, and you can see here the number of ancilla qubits is really, really big. Complexity class-wise, this is no problem. We can definitely do this easily, but in practice, this costs us a lot of qubits. In simulation, that's bad. And the number of gates is quite big in absolute numbers, at least, which makes it really not NISQ friendly. Okay, so one shortcut that could be taken in order to get out of there is, instead of doing this whole operation here, including the ancilla quantum encoding and the preparation and then the uncomputation in the end, is lookup tables, actually. So you just think about, okay, which is a function that I actually want to apply, here being f, and then I see, okay, which is the input that comes out, and given that input, how would the output look like? I pre-compute that, basically. This will be the angle here then, and then I get this with the rotation, basically, for free. The catch for that is, of course, it's exponential in complexity, because, you see, we need to do all these combinations of Toffoli gates, basically, and the Toffoli gates. Which is simple in theory, basically, to be done, but in practice, of course, the scale's just way out of hand. And we thought about now, okay, this is a nice idea. We can, complexity class-wise, maybe not cut it better, but it's very much more simple. And then in the next step, we took inspiration from polynomial rotation circuits, which aren't for arbitrary functions, basically, but for specific polynomials. So let's assume we take in here x1, x2, x3, and we have our ancilla qubit here, and then basically these or this circuit here can apply arbitrary polynomials on those inputs x1, x2, x3. It's still exponential, but the cool thing here is now the controls are quite a lot smaller in the number of qubits involved, basically, and usually the angles are also a lot smaller, and more of them contribute. It's not just one gate for one input, but for one input, multiple gates can fire, basically. And this has already been done. There's some implementation out there in Qiskit that you can find here below. Then our idea was, if we look at some example of this, there might be very, very small rotations in there, indeed, for some given polynomial rotation, which we can just cross out, just like that. And of course, we get a small error, but in practice, actually, this error isn't really all that big. And the ratio of gates that we can cut out can be quite large. So the efficiency of this approach when pruning out those small angle rotations is really good. Okay, so seeing that this works for polynomial rotation circuits, we can now look into how this works for LUT circuits. And actually, we can follow a very simple procedure which we implemented and is available, as you can see on the next slide then, to transform these kinds of LUT circuits into a form of rotation circuits, but still implementing arbitrary functions. So just to give you an intuition about this, let's assume we look into the first one here. So if everything is 0, only this gate would fire. And if everything is 0, also only this gate would fire. So those two will have the same value. So now if we already have the value right for the 0, 0, 0 state. So for the 1, 1, 1, 0, 0 state, now I have to see, okay, what do I have to correct about the one that I already have before that? And this is how you basically go through all of the different combinations. Is it still exponential, of course, but with this approach, yeah, we can get those LUTs in the form of rotation circuits, which then, in fact, can be pruned. As promised here, the algorithm is quite simple. We have an implementation of that online, even including the prunings, of course, where the prunings can be, yeah, specified to either like have a maximum circuit size that you want in the end, or a maximum error bound that shouldn't be exceeded. So yeah, the thing is, it's exponential actually in computing this, of course, because there are exponentially many gates, but this will only be relevant in a small scale NISQ era, basically, where we don't have so many qubits, and also this can be pre-computed classically. So if we know which function we want to apply, which is the case in the HHL, then we can just do it once, and computational costs can be seen as constant, basically. Okay, let's get into the results then. For very easy functions like this cubic polynomial here, or monomial actually, we can see that the gate count here on the x-axis and the largest absolute error yeah, basically form differently depending, of course, on the number of qubits n here that I use for displaying this x basically, or having precision for this x. And in the interval for x being between minus 0.5 and 0.5, we can see that actually we can get very good errors already with a small number of Toffoli gates in total. So you can always see that basically, depending on how much error you want and how many qubits you have, yeah, what's the best fit for this with these results here. So yeah, there can definitely a lot can be pruned probably if you don't need so much error. You can definitely get down like an order of magnitude, for example. Going on to some more difficult functions like sinusoidals, we can look at the sine function. There, the curves look a little bit different, but overall we get very, very small errors. So there, like if we really need the precision of 10 to the minus 15, then of course we really need those 40,000 Toffoli gates here for n equals 12. But if an error of 10 minus 4 already suffices, then it's just a couple of thousand maybe. So there can be, yeah, immense decrease in circuit size, basically. Going on to the next function with exponential functions, we can see basically similar results. Going even further and back to the HHL, this would be the function that we would actually have to apply in the HHL. Those two arcsine of some constant scaling factor, basically, that scales with the number of qubits that we use for the precision. And then, of course, 1 over x to do the actual inversion. Then we can see, okay, this function really doesn't scale so well. So in this case, we really need a lot of gates actually. The pruning doesn't work so well, and mostly this is of course with this factor of 2 to the minus n, which can get very small, and also x in the reciprocal form makes quite difficult values to compute. On the other hand, if we just look at the arcsine function, it gets way easier. So HHL really is a form that's quite difficult here. And if we can see, even arcsine has its own problems, but if we reduce or rescale basically the x variable here from the interval from -1 to 1 down to -0.5, 2.5, we get a much nicer curve. So a nice insight here is that rescaling in the beginning can already help you quite a lot. All right, exactly. And then, just to get some practical numbers in for this, we also use the arcsine function, looking at different numbers of precisions. And in this case, we did a polynomial approximation of that. So with d denoting here the degree of that polynomial. And on the left is basically the naive polynomial decomposition that you could do. In the middle is when you then cut out the 0 rotation gates, so rotation gates with angle 0. And then our approach with pruning involved or give an error up to 10 to the -3, so 3 points after the comma basically. And there you can see it's definitely a trade-off between number of qubits involved and also the approximation degree. And if you have a lot of qubits actually and a high degree and that approximating polynomial, there we can really prune a lot of values. So from originally up to like 40,000 to fully gates, you get down to maybe a couple of hundred, few thousand. So really orders of magnitude better. All right, and that's really realistic scenarios, like 12 qubits. That's definitely something that we can imagine going on into NISQ or like early fault aware quantum computing basically. All right, then already let me get to the conclusion basically. So quantum and ancilla encoding benefits immensely from pruning, but of course it depends on the function that we are looking into. But yeah, definitely our LUT adaptation basically allows for lower number of qubits in ancillas, basically for the HHL, which makes it way more NISQ friendly, and also the small low error circuits in the most cases that we looked at are also very beneficial for this approach. For future work, we would be certainly very much interested in seeing how applicable our approach is for other HHL extensions. Of course, HHL is also not the final best version of quantum linear systems algorithms that are out there, of course. So maybe we can see into like the realm of quantum signal processing if there's also something that we can do there. Beyond that, there's a paper, for example, using the AQE called quantum speedups of Monte Carlo methods, which might be a nice application basically of the approach that we have developed here. And then, of course, pruning techniques here showcased high potential to make things a lot more NISQ friendly. And it would be interesting to really explore in the future as well what these kinds of techniques can maybe also do for other algorithmic subroutines in the quantum realm, apart from AQE. All right, with that, I'll conclude the section just acknowledging our funding we got from the Q-Challenge project and the BMWK in Germany. And I'm now open for some questions. Thanks so much.